Okay, my name is Chung-Kai Lin. I'm from TSMC Modeling Group, and we are going to talk about SPICE model today. And however, before I get into details, I would like to share with you one of my stories. And the first assignment I have assigned by my first manager in my career, actually, he gave me one document to read when I get on board to my first job. And that document actually is written by Larry. I believe that is your dissertation. That's the memorandum 520. Yeah, so that's the first document in my career assigned by my manager. I need to read it. So ever since, I have been working on the SPICE-related project since then. So actually, Larry's dissertation is the key to open the door for my career. Yeah, so thank you. And and actually, I was so happy when I see I never talked to Larry before, and when I see the conference arrangement, I know Larry is going to be here, and actually I wrote an email to him and introduced myself. And surprisingly, I got a reply from him. So I was so excited that particular day. And then I jumped up and down in my office and then shared the email to my engineers in my group. And then nobody knows what's going on. And then they just know their manager is so happy that day. So that's great, all right? So we hear a lot of interesting story introduced by Larry, and now we are going to talk about current SPICE model we are doing. So it's slightly different from the direction Larry get into, but here we go. Okay, so today I'm going to talk about the role of campaign model in, say, TSMC. And then I'm going to talk about the ideal model versus engineering model. What's the difference? What kind of trade-off we need to do when we're making a model? Then I'm going to talk about the extension needed for the standard primitive model. Okay, and the final topic I'm going to talk about TSMC model interface, TMI. I talked about this one last year in Denver a little bit. Hopefully, I can have a longer time to talk about this today. And actually, we made a big progress in this year for FinFET modeling. So that's the material, that's the content I would like to share with you today. Okay, the role of campaign model. So usually, designers have their own design spec. So based on their design spec, they need to do tape out. Before they tape out, they have to do a million of several times of simulation. So the model provided by foundry needs to be reasonable, accurate, but needs to be efficient. Okay, so otherwise, people cannot do so many simulations they want to do. So the keyword currently for our model is reasonable, accurate, and it must be efficient. So that's the goal we try to achieve today as a SPICE engineer. Okay, so that's the brief introduction, the level setting for the campaign model. So let's talk about the ideal model versus engineering model. This is the general model flow. I think every SPICE model engineer pretty much do the same kind of flow to create their model currently. So the first step, we need to pick up the silicon and then do the silicon measurement. Assume we can do a perfect measurement. Then we need to do curve fitting. We have to extract the critical parameters and then build out a model based on those critical parameters. Then we need to center our model away from silicon, since sometimes silicon is not on target yet. So we need to purposely make our model away from silicon. Okay, then we need to do the temperature. We need to extract the temperature coefficient, and then we need to do the corner model to cover the worst case. Then we need to do a lot of add-on features on the model. For example, the layout effect, the statistical features like aging model, self-heating model, those kind of stuff. Okay. Then finally, before we release our model to the end users, we need to have a complete model QA to make sure there's no stupid bugs in our model. So basically, that's the flow for the model generation. So in the next few pages, I'm going to talk about one particular issue happened in this process. Okay, so the first step is to find out which silicon we need to use for modeling. So this is one example. This is one particular parameters. This is another parameters. Okay, so this is the silicon distribution. Okay, and this is another set of electrical parameters. So another distribution taken from wafer directly. So there are 2 points here. The green dot actually is the technology target we are going to achieve in the future. And the red dot here actually is the median for this set of distribution. So for some cases, the technology target and the technology median is close enough. So it's no issue for a SPICE engineer to identify so-called golden die for model iteration. However, for sometimes, especially for the early stage of technology development, the target actually could be away from silicon. So there's a gap here. So when we pick up the so-called golden die for model iteration, we need to think about, are we going to pick up the golden die from median, or are we going to pick up the golden die based on the target? So that's the issue we need to think before we do the silicon measurement. Okay, so sometimes, because for this one, it's like in the tailoring distribution, it's not typical enough to represent the silicon we are going to do the model. So sometimes this could not be a good choice. However, if you do the model based on this point, then you need to do a lot of centering to center your model to this green point. So then, again, they will break down your model as well. So you need to think about how to do it. So I would say when we do this kind of judgment, that depends on a few factors. One is the silicon maturity. The other one is the application driven. You need to understand what's the purpose for this model. If the purpose of this model is for to understand the sensitivity for the future target, then you may want to just do a target-driven model. However, if you need to, if you want to build a model to under the current performance, then you may want to build a model based on the red dot here. So I would say that the decision making actually is case dependent, is application-driven decision. Okay, but sometimes we also rely on the TCAD, the help from TCAD. The TCAD, because sometimes this green dot could be even far away from silicon. There's no way you can touch the silicon at all. So under the kind of situation, we need help from TCAD, and TCAD will help us to create the IV curve for model parameter iteration. Okay. And the next issue when we do the parameter iteration, and then we will run into a trouble. Say we have too many targets to fit. Usually we will have a few different anchor points for the on the IV curve for model building. For example, we have saturation current, the current current for saturation region, and the current for the linear region, and then current for like threshold voltage, leakage current, and so on and so forth. So we have quite a few anchor points to describe the future IV curve. So as a SPICE engineer, sometimes we have hard time to meet all the anchor points in one model. So what are we going to do about it? So usually we will discuss with our user to understand what is the need for this model. So usually for the first order parameters like saturation current, leakage current, and threshold voltage, we can do a pretty good job to make sure our model can meet silicon behavior. However, for the second order parameters like transconductance, like GM, GDS, we may not be able to fit to silicon 100% correctly. So like Larry says, sometimes people has too much trust on the SPICE model. Actually, they worry me a little bit. Yeah, because SPICE model do have their own limitation. Okay. And actually, 2 pages before, I was talking about the centering. So this is one example for centering. You can see the silicon actually is dash line here. And the starting line is model I'm going to offer to our customer or our users. So we know in the future, this is the goal for future silicon. Although I got the silicon here for model building, after I fit the silicon, I need to move the model to this line on purposely. So basically, I try to make a good model become a bad model. All right? So, but when we do that, we need to have other information to help us. For example, we need to understand what is the correlation among different parameters. Sometimes the VT may not be on target yet. So when VT goes higher, the leakage will be lower. The current drive will be smaller. So we need to talk to our device engineer a lot, then understand what are they going to do in the future to bring the silicon to the future target. They will tell us sometimes they are going to do the mobility boost up. Sometimes they told us they are going to do like a VT tuning here and there. So we will use different sets of parameters to tune our model away from current silicon and meet the future target. So that's what we do every day. I mean, we talk to our integration guy, we talk to our device guy to understand what they are going to do in the future. Then we can do a better guess for our so-called target-driven model. Okay. Okay. So this page, I'm going to talk about ADAM model, and among all of those ADAM model, the corner model actually is the most interesting one. And actually, in the coming technical program tomorrow, we are going to present one paper about the Monte Carlo simulation. And so you can look at the silicon. This is the silicon distribution. Again, the parameter 1, parameter 2, parameter 1 again, and parameter 3. So you can see a few spread among between the parameter 1 and 2. So as a model engineer, we need to tell our users what is the worst case for the process distribution. So we need to do so-called typical case model and the worst case model. Say, for example, I call this one as the fast corner that represent the faster silicon. And this is a slow corner. They will represent the slower silicon. So to provide the corner model, or so-called worst case model, circuit designer can understand what's the worst case for their design. So they can put enough margin on their design to make sure their design work in the future. So what's the difficulty for the corner model? When we do corner model, actually, we want to skew parameters, skew spice parameters. For example, to do the fast corner, usually we will make the oxide thickness thinner, and the gate length shorter, and the gate width wider to represent the fast silicon. And for the slow corner, we did the same, but in the opposite direction. So it sounds reasonable to do so, but it usually creates troubles. Why? Okay, so listen to me again. For the fast corner, we make oxide thickness thinner. So they will be fast for DC, but it will increase the amount of capacitance. So actually, they will make capacitance loading higher. So in certain way, it's not a fast silicon at all because the AC loading is higher. So you can see there's a conflict between the corner parameter, the skewed parameter. Basically, there's conflict between DC and AC. So usually, I would say there's no universal corner to meet all the criteria. So you need to create application-specific corner. For example, the worst case of ID set may not be the worst case for GM or GDS. So in other words, you need to create the digital corner and also analog corner because they represent a different set of silicon. But sometimes designers don't like it at all because they need to use like double effort to do the worst case simulation. So sometimes they will tell us, why don't you guys to create a compromised corner? It describes the fast silicon not that fast for digital and still good for analog design. So actually, so they create a lot of trouble for a modeling guy. All right. So sometimes I will tell them, well, there's no such kind of corner in the world. So just do Monte Carlo simulation. But when you do Monte Carlo simulation, actually the runtime will increase a lot. It's not only n squared, it will be more than n squared because there are so many simulations you need to do. So that's the trouble for the corner model. Okay. Okay, so that's basically a few issues for the general model modeling flow. We do have an issue for the silicon selection. Then we need to compromise between different parameters. Then we need to destroy our model from good model and make it become a bad model, because in the future the silicon, anyways, the model is to represent the target. It's not represent the current silicon. Then we need to create a corner model, and unfortunately, this corner model is not universal. Okay, so in the next few pages, I will make the situation even worse, because we need to do a lot of model that try to cover the effects not described in the current primitive model. Okay. So this is the intrinsic MOSFET I would say. So on top of intrinsic model, we have again, primitive model enhancement that will cover the gate-induced diode leakage. Then starting from BSIM4, for example, they do have a gate current model here. So pretty much that's the so-called intrinsic model. It behaves okay for a regular transistor. However, there are some effects due to manufacturing that cannot be covered by standard primitive model. For example, the drawn width is not, the final drawn width is not the same as the layout engineer drawn because of rounding here due to OPC. So we need to add effective gate width over here to describe the real effective channel width. Then this one actually is environment dependent. So we need the help from layout proximity iterator to help us. So you see that the boundary between transistor model and the layout iterator actually is no longer exist. That these two actually mix together already. And for when you do an implant, the dopant cannot go to the location you want to implant anymore. So they scatter around, so that there are some new effect, which may not be new anymore, but used to be new. It's well proximity effect. So we need to have use subcircuit. We need to have subcircuit and on top of primitive model to describe it. Okay, and there are so many stressors. So there's a STI stress effect, and this famous LOD effect, length of OD effect. So all of those effects, you need to have a subcircuit on top of primitive model to make the model close to silicon. So the equation, the equation of primitive model may not change that much. However, we need to use a very complicated subcircuit on top of primitive model to make sure our model can reflect the silicon. And actually, there is a lot of simulation time because you do a lot of crazy equations in the subcircuit. So they slow down the simulation a lot. Okay. And also, when we talk to the designers, usually they have some requests. They need to have, say, like I say, they need to have a feature to predict yield. So we need to have a statistical model. So this is the statistical model we have to do. So we need to model the process variation. We need to do the mismatch model. Combine these two, we can do yield prediction for the SRAM, for example. Then when we build a model based on this transistor, that's the regular transistor. But when you connect two transistors together by the state gate configuration, so there's no connection out of it. So you need to make sure there's no double count for the resistance here. So this is a typical connection for the SRAM. So under the kind of situation, we need to build up a special model, or we need to remove some component out of intrinsic model and let the layout iteration tool to handle those components to prevent from double counting. Okay. And also, people overdrive their application a lot recently. So usually people will consider aging model, reliability model. So we need to create a durability model for agent simulation. So those are the features requested by our customer or by designers. And those features actually is not available in the primitive model. So there are a lot of enhancement we need to do. So to make this enhancement handy or make sure the model can be finished within a reasonable time with the reasonable accurate, we kind of start a new project. We call it TSMC model interface. We start this project like in 2007, if I remember it correctly. There's 6 years ago. So we create this TSMC model interface. And so why and what is TMI? So we understand the limitation of sub-circuit approaches. First of all, the simulation efficiency is not good. It is the burden for primitive model. And usually it is not flexible enough. And they created a huge gap between pre-layout simulation and post-layout simulation. And it's not portable. I mean, from simulator to simulator, from HSpice to Spectre to Aldo, it's not compatible, especially for the sub-circuit. Every simulator have their own syntax. So it's a nightmare for model engineer because we have to do model in multiple formats. Then we need to QA our model to make sure the outcome among different transistors are identical enough. So this is a huge nightmare for my engineer because that we need to use a double or triple resources, do a lot of tedious stuff. Then if there's a trouble, when we talk to the EDA vendor, and usually our vendors say, how come their tool is more accurate than my tool? I think my tool should be golden. So I'm not going to fix our tool. Just talk to the other vendor because we think the trouble is from other vendors. So we need to negotiate among different vendors to make sure finally we got the identical result. Okay? So this is the nightmare for model engineer. Okay? So to fix those issues, we created TMI, the TSMC model interface. I call it as a unified solution. And it's also approved by CMC, Compact Model Council, and release it as a standard. So I will go into detail in the next page. So TMI actually is not a model, but there's an API that's for compact model extension purpose. And that's in public domain. So everyone can use it. So we co-work with EDA vendors and then share with them our spec. And then they create API for, we work on the same API. And then when they follow the protocol, then we can create our own equation, our own model, and plug into the commercial tools. So actually, they enhance the simulation efficiency quite a lot. Okay? And then also, it can apply to all the standard models like BSIM4, BSIM-CMG, and HiSim, whatever you want to do it, they can do it. Because it's not a model, it's the application interface. Okay? And it's backward compatible with all the existing macro model. And also, TMI enabled the foundry model team to provide better model for advanced process technologies. So if the primitive model is not good enough to describe your silicon behavior, you can always use your own equation and build it into a TMI and compile with API, and then you can have your own model. Okay. So this is the simple cartoon. Then you can see what TMI can do. For example, flexibility. It provides flexible usage for FinFET. Usually when you go to the FinFET simulation, people will struggle. What kinds of impact, what kinds of input I should use for FinFET simulation? Is the footprint or the width, or the input should be the fin number, whatever. I mean, but in TMI, we can make it all flexible for different users, for different purpose. And then, as I mentioned, due to different layout dependent effect or environmental effect, usually people will see a huge gap between pre-layout simulation and post-layout simulation. So TMI actually can do a much better guess for the pre-layout simulation. So people will find that in the TMI, the enhancement in TMI actually can reduce the gap between pre-layout and post-layout. And that's a very welcome advantage provided by TMI. And compatibility, because the primitive model is the same, so we don't need to go through the subcircuit anymore. So it's compatible among different commercial tools. That's the beautiful part of a TMI. So it actually reduces our loading a lot. Okay. Then efficiency. Since that is it's not subcircuit, it's the code, the new equation has been compiled into the commercial tool. So it can integrate with the commercial tool better. So the simulation time is shorter, so it's much more efficient. And also, the memory allocation is much better. So as far as we know, use TMI, the model can be used for much more. The number of transistors can be simulated is much more compared with subcircuit. Okay, and here, expandable. Like I mentioned, sometimes people will ask the agent model, and the agent model actually cannot be enabled by subcircuit. You need to have a special tool to do the agent model simulation. So, but with TMI, the SPICE model can actually, the agent simulation can be done by SPICE simulation. And also in the future, for the FinFET, a lot of people worry about the self-heating. And actually, self-heating can be done by TMI because TMI can integrate the waveform and then calculate the power dissipation during the application. So the TMI actually make the simulation much easier, and provide a different kind of simulation features. So it's one more step. We try to push the simulation capability one step forward by TMI. So basically, that's the concept of TMI. This is the simulator, say the HSPICE, Spectre, Aldo. And then there's API between TMI and the simulator. So we can do a lot of pre-process for the SPICE parameter by our own equations. Then after we modify those parameters, and then we send it back to the simulator, so simulator can see a lot of new information built by model engineer. So this new equation just integrate into the commercial tool. Then a lot of information you can also obtain from this interface. Say, like I mentioned, the waveform. You cannot do that in the past by subcircuit, but currently through TMI you can do the integrate. You can calculate the way you can integrate your power dissipation or integrate your effect by different way based on different waveform and through TMI. So that's the comparison here. So traditionally, we do model based on silicon and then put into model car, then do simulation, that's all. You cannot do anything. However, currently, And actually, now in the future, when you do a model, actually you create the information database. And that in that information database, you can talk to different tools. You can talk to LVS, and you talk to simulator. Actually, you can integrate with PDK, process design kit. This can help you to help designers to get a lot of information out of simulation. Okay. So this is the standard model, traditional primitive model. There's a lot of effect inside, like mobility, like a quantum effect, a short channel effect, those kind of stuff. I mean, you can see it in the coming 3 days in this conference. You will see it. And this is the core for the primitive model. Then on top of this core, TMI just cover it with additional effect here, like a different layout effect, layout dependent effect, and also we can unify our statistical feature together in this model. We can do the local variation simulation, global variation simulation, and we can also do the high sigma sampling for the SRAM. Then we can do a lot of parasitic modeling, and we can integrate the front-end device, middle-end device, and back-end information together through TMI. Then we can do the waveform integration and then get the agent model going, and in the future, even self-heating model going. It's become possible. So this is a total solution to meet design needs in the future. So here is my summary. So the company model actually is bridge between silicon and the design. So the model has to be accurate. However, it also needs to be efficient. Okay, and and so we need to build up engineering model, but we need to respect the ideal model, the ideal derived from ideal model. Okay, and then we do have some major challenge for transistor modeling. This layout dependent effect. We need to do the good variation modeling, and then we need to take care of parasitic component. Then we need to enhance our model, make it and can do the reliability modeling. And finally, we think we need to have a unified model platform to customize model on a common standard. And what we did in TSMC is we create a TMI then to try to enable all of those details into the current complete model. So that ends my talk today.